screen, right?
Yes, sir.
Today we'll be talking about unsupervised learning. Okay, so far what we have talked about supervised learning. And in supervised learning, let's say if we have these training data, and you can see from the illustration that let's say these samples belong to one particular class, and these samples they belong to another particular class. And then if our objective is to classify them, okay, so what we are going to do? We are going to draw a decision boundary where basically if we draw a decision boundary like this, something like this, so where the value of z will be equal to 0, that is where we have the decision boundary. And then later on, if we use this segment function on this value of z, basically we get the probability of the sample, okay, falling to one particular class given x, right? So already this is what we have seen so far. Supervised learning means the basic thing is that we know the class level. That in this one, let's say this one belongs to class 1, this one belongs to class 2, and so on. Because of unsupervised learning, you can see from this data, we don't know which sample belongs to which class. Like if we look at the previous case, we can see that for each corresponding sample, we know the class label given in Y. And now we can see that in case of unsupervised learning, we don't have any class label. That means we only deal with this data set, nothing else, okay? And from here, basically what we have to do, we have to detect some patterns in the data, which is there, but which is not given actually, okay? So this is what we have to do. We have to detect patterns in the data set, but the thing is that the ground truth or the class level or the actual output or actual, what can I say, the value that is expected is not given, okay? So this is what you have to find it out. Okay? In case of clustering, if I want to do some clustering over here, let's say how many clusters will you say will be here?
2.
2, right? Let's say someone will say, okay, this is one cluster and this will say another cluster, okay? And this clustering can be used as a pre-processing step for further processing, okay? So the basic thing is that in case of unsupervised learning, we have to find the inherent pattern in the data, okay? So from this we can see the definition actually. So that means unsupervised learning means we want to take undirected patterns in the data where the labels will not be given and there will be minimum human supervision, okay? So we want it to be automated, okay? For example, in this case, maybe it can happen like you have some more samples here, for example, okay? Something like this. So in this particular example, if I say how many clusters are there? So what do we say? How many clusters are there? So one may say, okay, here we have one cluster, here we have another cluster, we can say like that. Or maybe someone can say, that, okay, here we have one cluster, here one cluster, and then here we have another cluster. So we can say that, okay, we might have 3 clusters over there. Okay, so that means if we need some human intervention over here, we might want to define how many clusters we want. Okay, so that's why we will see over here that we want to do unsupervised learning with minimum human supervision, but time to time we'll see that we'll need some human input. Okay, so the main 2 methods basically we'll be seeing in unsupervised learning is principal component analysis, which is known as PCA, and the other one that just we have talked about is the cluster analysis, where we want to find and group the data into different clusters. Okay, so we know about clustering analysis. That is, we have seen the example that when we want to learn group them, okay, to group the data or to segment the data in such a way that they will share some common attribute value. Okay, they will common some attributes. So basically, this attribute means basically this is some attribute. We can say attribute value. Okay, but in case of principal component analysis, so we'll see that it's a new thing. It's a learning strategy where from the old feature space we want to move to a new feature space so that we can capture some characteristics of the data. Okay, by minimizing or maximizing one function. Okay, it can be some objective function that we want to maximize, or it can be some loss function which we want to minimize. Okay, we'll talk about this PCA very soon. So today's lecture is basically on PCA. Though we are saying that the main 2 methods in supervised learning are PCA and clustering analysis, there are a lot of other different kind of unsupervised methods. Okay, so since in this lecture we'll be particularly talking about this principal component analysis and cluster analysis. That's why I just pointed out these two parts over here. So up to this, is it clear?
Yes, sir.
So as I've said, so already you have the basic idea about clustering analysis. That means we want to cluster them into groups, something like this. Okay, something like this. So if I say in this particular example, if I do clustering, how did you cluster them? In what criteria have you clustered them? What will you say?
Based on proximity.
Yes, based on physical proximity, right? Yes or no? So this is actually what we have done. That means we have brought out some clustering criteria. Okay, so in this case, you will see the interest of clustering analysis, you will have to have some clustering criteria. Okay, based on which basically we will do this grouping. Okay, that means we'll group this group or we'll do this segmentation. But now we'll talk about principal component analysis. So from the term, we can see that here what they have focused on, they have focused on principal component. Okay, so what does principal component means? Principal component means basically for a particular set of data. Let's say if I have given you this particular data over here. Okay, so that means we are talking in this 2D feature space, remember. Okay, so the principal component is basically the direction. Remember, this is the important thing. Principal component is basically the direction which best fits the data. So doesn't it seem similar to regression, linear regression? Yes or no?
Yes.
Does it look like linear regression? Yes, right? But the thing is that since we're talking about this, let's say if I generalize it for this n-dimensional space, okay? That is, you are dealing with the n-dimensional feature space. So in this case, what we want to do, okay, so in this case, let's say they have used this notation P, okay, this P space, P-dimensional space, okay. So here we have talked about these principal components, okay, principal components, that means we want to find a set of directions which will basically best describe the data, and you will see that each of the directions, let's say if I take one of the directions in this direction, you will see that another direction will be in that direction. So you will see that the first principal direction is perpendicular to the other, right? Yes or no?
Yes, sir.
Okay. So if we are talking about this, let's say if we are talking about 3D space, the third principal axis will be in which direction? The third principal axis will be in which direction? It will be perpendicular to both this one and that one, right? That means it as if there is a vertical line that is pointing towards you. Yes or no? Do you get the point?
Yes, sir.
Okay. So, but if I just simply talk from this for this 2D space, for example, if I simply talk from this 2D space, so in this case, what do we have? We are having basically the best fitted line which minimizes the square distance from the points to the line. So it seems something similar to regression, okay, linear regression, but it's not same. We'll see the difference, how they're going to be different, okay. So this is what we are talking about, principal component. And if I say principal component analysis, what will it mean? What do you think? So if I want to say, now I want to analyze them. What will it mean? First of all, the first task will be to find the principal components, right?
Yes, sir.
And the second task will be to use this principal component to further analyze the data. Okay, so this is basically what we're going to do. And how do we further analyze the data? In this case, basically what we'll do, we'll try to reduce the feature dimensionality. Okay, is this clear? Yes or no? Okay, let's move on. So PCA. So basically PCA is a process of computing the principal components. As I have said earlier, we want to find the principal components, and later we will try to use these principal components to change the basis of the data. Okay, the basis of the data means basically what we'll talk about is basically we'll change the representation of the data. Okay, representation. Okay, representation of the data. PCA in signal processing. Okay, those who have completed signal processing. Did you come across this term, KLT transform? KL transform? Yes or no?
No.
Anyway, so PCA in signal processing is also known as KLT. Okay. And this is basically one of the popular techniques for multivariate data analysis. It was first proposed by Pearson in the 1901. Okay, but it was independently also proposed by Hoteling in 1933. Okay, so that's why you will see that both of the name will come up whenever you see who invented PCA. Okay, the thing is, as I've said, since we want to change the basis of the data, you see that if we want to analyze the data, we see that we can use PCA to reduce the data dimensionality. So this is basically very important. Okay, so that means we will see how can we reduce the data dimensionality, and how does it do it? Since we want to find the basis, the new basis of the data, you will see that the PCA will try to find the principal components. That's good enough. We have understood this one. But how it does, it basically what it tries to maximize the variability in the data. That means it will try to maximize the data variance. Okay, this is what you see variable. We will try to maximize the data variance. Okay, so this is the main important thing over here. Okay, after this, do you have any question? No question? Are you listening to me?
Yes.
Okay. Just a minute. Where am I? Okay. Next one. So do this projection. So that's why it is known as a linear. It tries to do. It will try to transform a set of correlated variables into a set of uncorrelated variables. Okay. Why can we reduce the number of variables? It is clear. And if you can reduce the number of variables, that means the number of features, what have we done? Basically, we have mapped the data from the high dimensional.
We cannot hear you, sir, properly.
We can't hear you.
Can you hear me now?
Sir, your voice is like cutting. Sometimes.
Okay, the voice is lagging.
Yes.
How about now? Is it good enough? No?
It's okay.
I think it's okay now.
Okay. So basically what I have said, so and once we have done data calculation,
Hello,
Can't hear you, sir.
sir.
basically we are transforming from a new old space to a new space.
Sir, we cannot
Okay.
hear you.
Sir, can you please repeat again? We couldn't hear you for some time.
Okay. Okay, I'm using mobile data. I think that's the reason maybe the
একটু কেটে কেটে আসছে স্যার
Shall I do that?
Sir, we can hear only one word and 10 words we cannot hear.
So I believe you can see the screen, right?
Yes, sir.
Out. Stop. Do you have any questions? Hello, can you hear me?
Sir, we're facing the same problem again. What happens is your speech gets chopped when it comes to our side.
That means whenever I'm sharing the video, it's can you see my screen?
Yes, sir. We can see your screen, sir.
Hello.
Sir, we can see the screen, but when you're sharing video, I think there's a problem with your audio. Then.
Okay, can you hear me now?
Sir, when you're not sharing your video, you can hear you just fine. But the moment you start sharing your screen, uh, your audio gets chopped off.
Okay. Then let's see. Let me try now actually see what happens. Can you see my screen?
Yes, sir.
So that now it will work. Okay. Okay, so we'll see how PC will do the rotation of the axis to generate the new data, and the new axis will be orthogonal, as we have said that we are looking for the principal components, and it will represent the direction of maximum variability. Okay. How is the audibility now? Is it good enough? Can you hear me?
Yes, sir, we can hear you, sir. There's still some portion of the problem still there, but I think it's manageable.
Okay, so I will go slowly actually. Okay. Okay, so we'll see here. So once we find the axis, so in this case, so one of you have to talk with me, okay? So that I will understand that I'm in the line. I'm not talking to. So in this case, if we have the data like this, so what do you think? Where would we have the principal component here? So we'll have the principal component in this direction. Okay. Is it clear? Can you see it?
Yes, sir, we can see it, sir.
Okay. So you see that all these points, okay, here we have like one point is here and there is there, another is there, okay. All these points are basically in the 2D space, okay. So this will be x1. So if I say this, these are basically your original feature values, which belongs to basically this 2D feature space. Now you can see easily from here. Let's say, for the time being, let's say if I say my line is this one for the time being. So if I project this particular point onto this line, where will you have this projection? Don't you think you'll have your projection over there? Yes or no?
Yes, sir.
And if I do the projection of this point on this line, you'll have your projection over here, right?
Yes, sir.
So in this way, if I do all the projection of these points onto this line, so basically you will have the projection after doing this projection. So all these points will be like this. And if I look particularly, if you look particularly from this point of, let me look when the points will look something like that below. Yes or no?
So in this case, are we doing an orthogonal projection on the line, or are we just taking the x value of the points and placing them on the line?
We're doing the projection. That's what I've said. We have done the projection.
Okay, sir.
We have taken only the single value. How would have it looked like? It would have looked something like this. Yes or no? But since we are doing the projection, your projection will look something like that. Correct?
Yes, sir.
Okay. So you see, okay, we'll talk about this very soon, don't worry. So if I have done all these projections, so this one project here, this one project there like that, all this projection, if I do this projection, then basically all this projection will look something like this, correct?
Yes, sir.
And then if you say after you have done this projection, you have got the projection value represented by z, then this projection coefficient will be represented by z, all those n number of samples, right? Now the projection value, does it belong to this 2D space or does it belong to a 1D space? Which one?
A 1D space.
So what does the representation change? That is question number one. If you do the projection on this line, on this, let's say if I say this is your principal component, okay, this is your principal component, does your representation change? Yes or no?
So I couldn't hear the last portion of it.
Okay, I'm saying that if I do the projection on this line, do we have a new representation of those points?
Yes, sir, we're reducing one dimension.
Okay, and second point is that did we reduce the feature dimension from 2D to 1D?
Yes, sir.
So this is the color we have done over here. So did we do projection over here? Yes, we have done projection, right?
Yes, sir.
And if I talk about this one, did we map to a higher dimensional space to a lower dimensional space?
Yes, sir, we went from 2D to 1D.
We did. Is it supervised or is it unsupervised? Did I say which sample belongs to which class or something like that? Did I say? I did not, right?
No.
So we have got this particular point. Fine. And then the thing is that, did we get a direction where we have the maximum variability? Did we get it? Or is it still a question mark? So now you see in these two parts, right? How did we get a set of uncorrelated variables into a set of uncorrelated variables, and you haven't seen how basically we get maximum variance. Okay, in this case, if I do like this, instead of taking this one, forget about this one. If I take this line as a projection line, how will you project? What do you think? So this point will project here, this will project here, this will project there. That means you will do your projection like this. Yes or no?
Yes, sir.
And then you will see that all these points, if I look totally from the point of this line, if I look like this, how will it look like? So if I go over here, how will it look like? Don't you think it will look something like this? All these points have been projected like that? Yes or no?
Yes, sir.
Yes, sir.
So, and then the variance of this data, is it large or is it small?
Small, sir.
Small. But if I did the projection on this particular line, so you will have all these points projected like that. And then after doing the projection, you see that if you look your data, don't you think you'll have something like this?
Yes, sir.
And how about the variance of this data? What do you think? Is it small or is it large?
It's large, sir.
It's large. So we have talked about the previous slide. That means we want to get the direction with the maximum variability. So I think we have got this point too, right?
Yes, sir.
So let's move on, okay? We'll see about data uncorrelation later. Okay, let's move on. So what would you think? What will happen if you do this principal component analysis in this 3D space? So the space is 3D, that's for sure. So what do you have to do? You have to find a space. So if you want to reduce from 3D to 2D, so in case of a single line, if I take a single line, let's say if I take a single line like that one, so how many projection coefficient will you have for a single sample? Let's say this is U1. So if you do the projection, will you get single coefficient value or you get multiple coefficient value for a single sample? What do you get? Let's say if I just simply pick one sample, the ith sample. If you do the projection on U1, what will you get?
So won't we get 3 values per sample?
No. For a single sample, let's say if I look at it from the point of 2D, this point is in 2D, X, let's say this is the ith sample, let's say this is the ith sample. If I do the projection on this line, how many projection coefficient, how many coefficient value do you have?
1, sir.
1. Okay, similarly, it doesn't matter whether it is 2D or 3D, same thing. If I pick a line, this is, like I've said, this is U, it's a line or it's a vector. If I do this projection on this line, how many projection coefficient will you get? You get 1, right? Yes or no?
Yes.
So let's say if I say this is U1, so I can say that I've got a projection value of Z1, right? Yes or no?
Yes, sir.
If I take a separate projection like something like that. So let's say this is U2. So if I project this point on U2, will you get a different projection coefficient? Yes or no?
Yes.
That is what? That is Z2. So that means basically, in this particular example, if I remove all these things over here, so if I take U1, if I do this projection, I will get a projection coefficient of Z1. Let's say if I have taken another, projection lines in this direction, that is U2. So if I do this projection on U2, what you will get? You will get Z2? Yes or no?
Yes, sir.
Previously, X belonged to this three-dimensional space. Now, once you have done this projection, okay, once you have this projection on the lines, okay, you have got this vector Z, and Z belongs to which space? 2D or 3D?
2D.
The vector Z,
It will be a 2D.
it belongs to the 2D space, right?
Yes, sir.
If we do this for all the points, okay, let's reselect. If we do it for all the points, don't you think it will look something like that after doing the projection? Yes or no? Will it look like that? At least with these two vectors, haven't I defined a plane? Yes or no? Did I define a 2D
Yes,
plane?
sir.
And all these points in the 3D space, all these points in 3D, if I do the projection on this 2D plane, don't you think all the points will now lie within this plane?
Yes, sir.
Okay. And if you totally want to look at the plane, don't you think that your points will look something like that?
Yes, sir.
Yes or no? Let's say if this, for this 2D plane, let's say the 2D plane that we're looking at, like we have said over here, okay, like we have said over here, the plane we're looking at. So if it is given by U1, so any point X, okay, any point X, if I project over here, I will get Z1. If I project over there, I will get what? Z2, right? Yes or no? So that is for single point. That point is this one. So if I look at from the point of, as I've said, if I look from the point of this plane only, I will get my Z1, I will get my Z2. So don't you think that you have reduced the feature dimension from 3D to 2D? Yes or no?
Yes, sir.
Okay, so do you get the point?
Yes, sir.
Let's move on actually. So the thing is that what we have done over here, as I've said earlier, we want to have a line, a projection line, and if I want to have that projection, I want to maximize the. If I do this projection of this point, if I pick a different color, if I do the projection on this line, how much information have you lost? Can someone tell me? Listen now, this point is represented in this 2D space. It has two elements. It will have this x1 and x2 element. Once you do this projection on this line, say x dash, okay, or let's say x dash now contains a single value, which is z. Now this x dash, this belongs to this 1D space. So how much information have you lost? Can you tell me? Don't you think that you have lost this much of information? Okay. So do you understand my question? How much information have you lost?
So I understood the question, but I don't understand how we got that answer. Are we calculating the distance as the information that was lost?
Okay, the thing is very simple. Let's say you have this. So simply from the point of this point, let's say this point is represented by 2, 1. Okay? So in the x-axis it is 2 units. Let's say what we say is x1, let's say this is what we have x2, and this is 2, and then this is 1. Yes or no? Now if this point, if I do the projection of this point on the x-axis, where will you be?
At x equal to 2, sir.
Okay, you will get the projection value of 2, right?
Yes, sir.
Okay, so if you have got the projection value of 2, then basically what did you lose actually? You lost this much of information, right?
Yes,
And what is
sir.
the value? The value in the y component, right?
Yes, sir.
Okay, that's very simple. But it becomes a little bit difficult when it becomes to something like this. Let's say you have this point, let's say this is your point 2. So if you want to do this projection on this line, so where is your projection value? Your projection value is here, right? Then how much information are you losing?
The perpendicular distance from the point to the projection.
You have lost that much of information. Because this part and this part basically gave you this particular vector, right? Yes or no? So if you do the projection, for example, whatever you have here, if you do the projection over here, basically now what you have, if I draw like this, it became different color. Including this vector, because I have this vector, you have now this particular part, but have you got this part now? Yes or no? So that basically this difference is called the projection difference or projection error. Do you understand what I'm saying? That means this is basically your projection error. Is it clear?
Okay, sir.
Now, if I look at from all the points, I can see the corresponding position errors. Maybe here, maybe there, maybe a little bit there. So if I take the summation of all those projection error, how much error do you have? You have a certain amount of error, right? Correct? Now, how about if I had taken this particular line, for example. So now if you have taken this one, so how much projection error will have? So first of all, I have to do this projection. That's fine. I will do this projection. Now, if I ask you how much projection error do you have for this sample, you have a projection error of this one, or this one, or this one, or that one, and then for that one. Don't you think the projection error is high? Yes or no?
Yes, sir. It's going to be.
Yes, sir.
So then the thing is that which one will give you smallest projection one, the green one or the red one? Will give you the lowest projection error? The red line or the green one?
I think the red one will give the lowest.
The red one.
The red one, right? The red one.
Yes, sir.
Okay. In terms of variance, which one will give you high variance?
Still the red one.
red one. So now if I look at what does PCA tries to do, PCA tries to find that particular direction, that particular principal component, which will basically give you the minimum projection error. That means basically this is going to be your principal. This understood?
Yes, sir.
Okay. Today we're going to have a very bad connection.
Sir, we have a classroom now.
Okay, so I have given you the link to your attendance. Okay, have you got it?
Yes, sir.
Okay. Okay, so I wanted to finish this whole lecture, but I couldn't go further because of this net connection probably. Okay. So thank you. We'll meet tomorrow, inshallah. Okay.